Have you ever just stopped and wondered, what is everything actually made of? I mean, what are you made of? What is your phone made of? What are the stars made of? Well, it's a question that people have been asking for thousands of years. And in this explainer, we are going to crack that code. We're diving deep into the tiny particles that build our entire universe. So let's just jump right in with that big question. What is the world really made of? Seriously, if you could zoom in, and I mean way in, past what any microscope can see, what would you find? What are the absolute fundamental building blocks of you, me, and everything around us?
You know, what's really wild is that this isn't a new question. People have been thinking about this for millennia. And the craziest part, different cultures, thousands of miles and hundreds of years apart, came up with almost the exact same idea. Way back in ancient India, a philosopher named Maharshi Kanad talked about Parma Manu. Then, over in ancient Greece, you had Democritus and Leucippus talking about atomos. Both of these words mean the same thing, uncuttable or indivisible.
So, how did we go from these ancient philosophical hunches to our modern scientific fact? Well, that's the journey we're about to take. We're going to start with that uncuttable particle itself. Then, we'll uncover the two golden rules that govern all of matter. After that, we'll meet the guy who put it all together in the first real atomic blueprint. And finally, we'll see how these atoms team up to build, well, everything. All right, first up, let's get a handle on this whole uncuttable particle idea. What exactly is an atom in the modern sense? And just how tiny are we talking here? So, here's the deal. An atom is the smallest possible piece of an element you can have that still behaves like that element. Think of it like a Lego brick of gold. You can't break that brick down any further and still have it be gold. It's the absolute fundamental unit that all of chemistry is built upon. And when I say tiny, I mean it's almost impossible to wrap your head around. Take a look at this number. That's roughly how many iron atoms are in just one small iron nail. They are so ridiculously small that you could fit millions of them on the period at the end of this sentence. It's just staggering. Okay, so we've got these bazillions of tiny building blocks called atoms. But how do they actually come together to form things? Is it just a total free-for-all, or are there some rules to the game? Oh yeah, there are rules, and we're about to learn the two most important ones. Rule number one is the law of conservation of mass. And honestly, it's pretty straightforward. It basically says you can't just make matter appear out of nowhere, and you can't make it disappear either. In any chemical reaction, you end up with the exact same amount of stuff you started with. It might look different, but the mass is the same. Nothing is ever truly lost. Here is a perfect example. If you take exactly 4 grams of hydrogen and react it with exactly 32 grams of oxygen, you know what you get? Precisely 36 grams of water. See? 4 plus 32 equals 36. Not a single gram more, not a single gram less. The cosmic bookkeeping always balances out. Scientists figured out a really clever way to show this. You take a sealed flask that has 2 different chemicals in it, kept separate. You pop it on a scale and get the weight. Then you just tilt the flask, let the chemicals mix and react, and weigh it again. And guess what? The weight hasn't changed one bit. It's proof positive mass is conserved. So the second big rule is the law of constant proportions. Now, this one sounds a little more complicated, but the idea is simple. Every pure chemical has a fixed recipe that never changes. Think about water. It's always made of hydrogen and oxygen combined in the exact same ratio. It doesn't matter if that water came from an ice cap, a jungle river, or your tap at home. The recipe is universal. Let's just stick with water for a second here. Check out this table. No matter how much pure water you have, whether it's 36 grams or 9 kilograms, the mass ratio of hydrogen to oxygen is always 1 to 8. It's the one and only recipe for H2O, and it is set in stone. Now, these two laws were a massive breakthrough. They described what was happening in chemical reactions, but they didn't really explain why. That's where this guy, John Dalton, comes into the picture. He's the one who connected the dots between these laws and the ancient idea of the atom. He basically gave us the first scientific atomic theory. Dalton's theory was so elegant and simple. He basically said, okay, all matter is made of these tiny, indivisible particles we'll call atoms. Atoms of one element, say gold, are all identical, and they're different from the atoms of other elements, like silver. And here's the kicker. He said atoms combine in simple, whole number ratios to form compounds. This idea single-handedly explained those two laws and laid the foundation for modern chemistry.
Now, was Dalton's theory perfect? No, of course not, but it was a revolutionary start. For instance, he took the ancient Greek idea of uncuttable literally. He thought atoms were the absolute smallest thing. We now know that's not true. We've discovered that atoms themselves are made of even tinier particles. You know them: protons, neutrons, and electrons.
He also had another idea that wasn't quite right. Dalton figured that all atoms of a specific element were perfect copies of each other. Same mass, same everything. But we later found things called isotopes. These are atoms of the same element that have just a slightly different mass. So while Dalton's blueprint was brilliant for its time, we've since added a few revisions. Okay, so we've got atoms, and we've got the rules they have to follow. So what happens when atoms actually start playing by those rules and linking up? Well, that's when we get to the next level of creation, molecules. A molecule is really just a team of two or more atoms that are chemically bonded together, holding hands basically. They can be atoms of the same type or different types. It's the next step up on the ladder of how matter is built. And really, you can boil it down to two main types of molecules. First, you have molecules of elements. This is when you have atoms of the same kind teaming up. A great example is the oxygen we breathe, O2. It's just two oxygen atoms stuck together. Then you have molecules of compounds, like water, H2O. That's when you have different types of atoms forming a team. In this case, two hydrogen and one oxygen. You know, chemists even have a word to describe how many atoms are in one of those element molecules. It's called atomicity. Sounds fancy, but it's not. Since an oxygen molecule has two atoms, we call it diatomic. Di for two. Ozone, which is O3, has three oxygen atoms, so it's triatomic. It's just a simple way to count them up. All right, we have covered a ton of ground. We've gone from ancient ideas to atoms, molecules, and the rules of chemistry. But how do scientists actually talk about all this stuff without writing a novel every time? Well, they developed a kind of chemical shorthand, a whole new language. Dalton himself actually invented his own set of symbols for the elements. You can see them here. They were these cool little pictures. But let's be honest, they were kind of a pain to draw all the time. So eventually, chemists came up with a much smarter system, just using one or two letters from the element's name. H for hydrogen, C for carbon, way, way easier. And this chemical shorthand is incredibly useful. It lets us do all kinds of quick math. For example, if we want to find the mass of a water molecule, H2O, we just look up the atomic mass for hydrogen, multiply it by 2, add the mass of one oxygen, and boom, you get a total molecular mass of 18 atomic mass units. It's that simple. So there you have it. We went all the way from a simple philosophical idea of an uncuttable particle, through the elegant rules that govern matter, to the building blocks of our entire reality. It's absolutely amazing to think that a few simple particles, following a handful of simple rules, are responsible for the incredible, complex universe we see around us. It really makes you stop and think, if they can build all this, what else are they capable of building?